welcome to Chapter 9. Chapter 9 is sort of a bit of a grouping of a couple different topics, all under the umbrella of what they call discrete mathematics. We are going to kind of be spending the first half of the chapter looking at some items that lead into mainly statistics and probability, because we're looking at combinations, permutations, and a formula called the binomial theorem that we're going to be looking at. All those things are going to would lead into statistics. As we look at the second half of the chapter, that's going to be more of a focus on a topic called sequences and series. Something you may have seen a little bit of in the past, but these are all topics that would lead into some other math areas and some higher math. So as you guys continue on in math, these are certainly areas that will come up again, especially in a statistics course, which many of you guys will end up taking, whether it's in high school or college. So all part of future math that you guys should be able to do. So here we go. So one of the first things that we're starting out with is looking at the idea of a combination of events taking place, right? And this is something that would hugely lead into probability. But they don't quite go that far in this chapter. This is more of a sort of lining up the basics here. So when it comes to combination of events taking place, in order to find out how many different ways something could happen, one of the basic approaches to this is something called the multiplication principle, where really simple, all that means is you simply multiply all of your options together to see how many total options are possible. So a pretty simple concept. So one thing you do have to be super careful of on this, and this is why we're going to break it up into kind of two different types of problems, is the very specific little wording that comes into play with each question, because it can really affect the way your combination gets set up. So in this first one, they're talking about license plates consisting of 3 letters of the alphabet, so obviously 26 letters in the alphabet, and then 4 digits, 0 through 9. So whenever you look at this, consider there to be 10 digits, right? 0 through 9 would be 10 digits. So we want to find the number of different license plates that can be formed. So look at the first part, and this is where I want you to notice the difference in the wording. So in part A, they're talking about no restrictions on the letters or numbers that can be used. In other words, what they're saying is you can repeat the letters and the numbers. So they could be all 9s, they could be all B's, they could be all C's, right? Whatever. So that's the case where things can be repeated, versus part B, which says no letter or digit can be repeated. And so that's super important that we pay attention to those little details. But really all we have to do is let's just lay out the scenario for each potential digit within the plate, whether it be a number or a letter, and then multiply them all together. So if there was no restriction, so in this case it did say that that 3 of them had to be letters, and then followed by, so the last 4 have to be digits. So let's just lay out the options here. So if the first 3 had to be letters, well then I have A through Z could go into the first item on the license plate. Second item on the license plate could be A through Z, so another 26, and then another 26, right? So A through Z are fair game on any of the first 3 items on the license plate. And then for the remaining 4, it just said it had to be a digit, so it could be anything from 0 to 9. So there's 10 items that we're looking at, right? And 10 items, 10 items, 10 items, because you're allowed to repeat them. So this value doesn't change as you go down the list because you were allowed to repeat the items. So as you multiply all this together, a whole lot of different license plates could get formed from that, right? And that's with some limitations, right? That's the limitation that these had to be letters and these had to be numbers. So there was even some restrictions on this, and it still produced a huge amount of options for these license plates. But here's what I want you to see is the difference on part B, where I cannot repeat any of the letters or numbers. And that's super important, because as I look at the first item on the list, so remember they said the first 3 had to be a letter. So for my first slot on the license plate, I have 26 letters to choose from, right? Well, after I pick a letter, when I go to the next item, now I'm only going to have 25 to choose from because I can't use the same letter that I've already used. Right? I have to pick a different letter. So now there's only 25 to choose from. And then once I pick a letter for this, well, now I only have 24 to choose from because I can't repeat either of the two that I've already used. And so you can see how this would just continue counting down for however many letters you wanted to use. And in this case, they said it had to be 3. Same thing with the digits. You started with 10, but after you use one, now you're down to 9, and then 8, then 7. So it really made a big difference in the outcomes, whether I could repeat or I could not repeat things that I've already used. So we really got to pay attention to those little certain words, like whether or not you can repeat or not repeat. You will see that this is basically a permutation. As you start counting down in values because you can't repeat things, that's exactly what we're going to see with a permutation. But we'll get there in a minute. Let's just do a couple for practice here. Let me start with number 3. So real similar situation, license plates with 7 blanks on them. They're going to give us a couple different scenarios. So I try to choose 2 that were a little bit different than the ones that we just saw up above. So in this one, the first blank is a letter, and the remaining 6 are digits that can be repeated. So easiest way is to just lay them out one by one the way that we saw up above. So we'll start with the first blank. It has to be a letter. So of course, there's 26 letters in the alphabet for the first blank on the plate. For the remaining 6, they have to be digits, but these can be repeated. So my second blank could be any of the 10 digits, any of the 10, right on down. That number's not going to change because I am allowed to repeat my values. So 1, 2, 3, 4, 5, 6. So we got them all. Obviously, that's 10 to the 6. You could write it that way if you wanted to. Right, we could certainly write it that way as well, but real simple. We could multiply that together, and that would be it. That would be the total possible number of license plates. So here's one just a little bit different. If all 7 blanks are letters that cannot be repeated, definitely something we got to take into account. So again, they're restricting this one to letters only. So as we look at these letters, I would start out with 26 letters to choose from. Since I cannot repeat them, it's just going to count down for each space. So I'm going to get 25. And then once those guys are selected, now I'm down to 24. 1, 2, 3, 4, 5, 6, 7. Right? And so what we're going to see down the road is essentially if I wanted to create this as a permutation, because it's counting down each time, we're going to look at this and we're going to say, okay, well, I started out with 26 letters to choose from. The P is for permutation. And how many are we actually going to select? Well, there were 7 blanks to fill, right? So the setup is going to end up looking like this. So that's kind of where this is headed. For now, they want us to just take this approach and just lay them all out one by one, which I'll tell you, this is a great approach because there's some pretty tricky setups that we can run into, and laying them out one by one like this is a great way to go. So it's a really good process to learn. All right, so before we get into distinguishable permutations, which is now what we are talking about, I want to show you something real quick at the top of page 629. Let me pull that up. All right, so let me first, before we even get into distinguishable permutations, let me just tell you what a permutation is. Permutation is an order of events. So with the one thing that you always keep in mind that qualifies something as a permutation is that there is an order to the process that you are doing. So like when we were doing the license plate, there was a first blank, and then a second blank, and then a third blank. There was an order to it. And so because things have to be done in a certain order, that's what makes it a permutation. And so what you're looking at right here that's highlighted in yellow is when they say n objects taken R at a time, that's exactly what I was talking about with this previous example when I set it up like this. So there was n objects, there was 26 letters in the alphabet, and they were being taken 7 at a time. That's our R value, right? So this is NPR. right? That's always a P for permutation, right? So R is how many of those you're actually going to place in an order, right? So that's where that notation comes from. Let me take you back to this. And so that's what makes this a permutation. Notice this always has to be true. R has to be less than n because n represents the total possible that you have to choose from. So if we were talking about the alphabet, I have a total of 26 letters, and it's how many of those am I going to be placing in order. If I cannot repeat them, and it's going to count down, 26, 25, 24, I can't take more than 26 and put them in an order if I only have 26 to choose from. So hopefully this is kind of an obvious idea, but that's just what they're talking about. So in a basic permutation would be the one that we were just looking at. And it does get into the idea of a factorial. Factorials are things where you are just counting down. So when you look at the last example that we just did, and we were doing 26, 25, 24, 23, 22, 21, that's what a factorial represents. And so if you were to actually take, I'll just write this down for you while we're talking about it. If you were to actually use all 26 letters of the alphabet, so if you kept going all the way down to 1, then you would write it this way. So 26 factorial means I am starting with 26, and I'm going to multiply all the way down to 1. But we only use this if you're going all the way down to 1. I couldn't use this in a case like this because I stopped after 7 items, right? I didn't continue going for all 26 items. In terms of a permutation, this would look like this. If I had 26 items, and I was actually going to put in order all 26 items, it would look like this, right? That's what a factorial represents. If you're going to take whatever this is, if you're going to put all of them in an order, then you have a factorial, right? That's what that represents. So if I had to create a batting order for my baseball team, there's 9 players in a batting order, right? Well, if I only had 9 players on my team, and I had to put all 9 of them in order for batting for a baseball game, well, I would have 9 players on my team, and I'm actually going to put in order all 9 of them for a batting order, right? My first batter, my second batter, my third batter, my fourth batter, all the way down to 9. So whenever you have that many objects and you're going to place all of them in an order, that's when you get a factorial. It looks like this. So that's what that notation means if you haven't seen that before. I thought they sort of leaped into this without giving you all that background information. So you kind of need to know what a permutation is. You also kind of need to know what that exclamation mark represents and to know that it does represent an order of the way of placing things. Here's one other word that I want you to see. Distinguishable. Distinguishable objects means they're all different, right? I'm not repeating items. And that's a big part of what a permutation is, right? That's why this was a countdown, is because I can't repeat something that I already had, right? And that's what causes it to count down to 1 less, 1 less, 1 less, 1 less, 1 less. So that's kind of goes in hand with the word distinguishable, is that they're all different. I have a different item here than I had here. So that's also an important part of this. So there's a lot of the background. So here's what's going on with the formula for distinguishable permutations. Distinguishable permutations means that I have to get rid of any repetition that I see taking place. So that's what the denominator represents. The denominator represents anything that you see that gets repeated. And I'll give you an example of this in a second. But that's what the bottom is. It's like we're dividing out, or we're taking out the repetition so that I'm left with distinguishable permutations, things that are all different. And the numerator is just simply going to be our total that we have to work with. So let me give you an example of what that looks like. So if we were to take the letters from the word Florida, and I just said I want distinguishable permutations. In other words, I want you to take all 7 letters from the word Florida, and I want to know how many different ways could you put those in order to create distinguishable or different words, right? Not real words. They could be anything, any combination of letters. So look at it this way compared to what we just did on the previous page. If I just said, okay, well, I got the word Florida. There's 7 letters, right? Florida. So if I were going to say, well, how many ways could I choose the first letter in a word? Well, there's 7 of them. So there's 7 different letters that I have to choose from. Well, as I go to the next slot, this is just like the license plate thing that we were just doing. As I go to the next blank to fill in, how many letters do I now have to choose from? I can't use the same letter I've already used, right? I want distinguishable permutations, right? I want things that are not repeated. I want different items getting used. So after I pick one, well, now there's only 6 left to choose from. And after I pick one of those, now there's only 5 left to choose from. And in this case, we're using all 7 of them to place in order, right? So if I really wanted to lay it out piece by piece, that's what it would look like. As we just talked about on the previous page, if you start with a total and you work your way all the way down to 1, then this is a way that you can write that. So I can write that as 7 factorial, which means this, right? 7 times 6, 5, 4, 3, 2, 1, all the way down. And so if you really multiplied all those together, that's what it would look like. And you should have a button for factorial in a calculator. On these, on my calculator, some of them have them on the faceplate, which is really nice if you have those. But not all calculators do. Sometimes you have to go into a different area. And in this calculator, it's under the math button. So if I hit math, and this is what you would look for in most calculators, if it's not on the front, it's probably, no pun intended, under that column right there that says probability. Because all this leads into probability concepts. So if I go over to probability, there's my permutation setup, there's my combination setup, and there's my factorial. Right? And so those are the ones I could use to type this into my calculator to get answers. Look at Alabama. Okay, here's something I really want you to catch on this. This is different, so pay attention. If I looked at Alabama, here's what you'll notice. This is what's different about Alabama than Florida. I mean, there's a lot different about Alabama than Florida, but as far as the spelling goes, Florida had no letters that got repeated, right? There's only one F, one L, one O, one R, so nothing got repeated. However, when you get to words like Alabama, we got some repetition in there, right? I have 4 A's that I'm looking at. So here's what's happening. If I were to say, well, how many letters do I have? 1, 2, 3, 4, 5, 6, 7 letters still? Well, with those 7 letters, if I said, okay, well, how many letters do I have to choose from for my first slot? And I put a 7 here. Well, that's not really true, right? It's not completely true because whether I choose this A or this A, I wouldn't be creating a new word, right? So I can't say, well, I have one spelling where I used this A first, and then I have another spelling where I used this A. That wouldn't make sense. I'd have the same word. That would not be a distinguishable outcome, right? It wouldn't be any different no matter which A I used. So when I go through this process, if there's repetition, I have to divide out the repetition because otherwise I would not have distinguishable permutations. So it doesn't quite work that way. So what you're seeing on this one is, and this is where that formula came in, on top, I'm still doing this, right? So I'm still going to say, well, I have 7 items, so 7 factorial is my total, and that's what goes on top. On bottom is the repetition. So because I have 4 A's, we are going to divide out 4 factorial, which gives me this result, and now I have distinguishable permutations from Alabama. If you get more than one repetition, like in the word Montana, I have 2 A's. I also have 2 N's. So you just throw in however many of those you need to divide out. So the top is still your total possible. So there's still 7 letters in Montana, so 7 factorial goes on top. And down here we're going to divide out any repetition that we would have. And those are being multiplied together. So there was 2 N's and 2 A's. So on bottom you have 2 factorial times 2 factorial. So if we divide out the repetition, that creates a certain number of distinguishable permutations. Let me give you one to try, and then we'll keep it moving. So as I look at the word coffee, total possible 1, 2, 3, 4, 5, 6. So there are 6 total possible. That's my numerator. On bottom, I have to divide out the repetition. I have 2 F's, 2 E's. So 2 factorial times 2 factorial. So that's getting divided out, and that could just easily go in the calculator using a factorial button. We wouldn't need a factorial button. I mean, I could do this by hand without a calculator at all. It really wouldn't even be that complicated. 2 factorial times 2 factorial is just 4. On top, I have 6, 5, 4, 3, 2, 1, right? That I could multiply together, divide it by 4. I could even cancel the 4s. Let me just show you this real quick. This is actually going to play into something we do later, so kind of wanted to show you. Here's what I got on top. 6 factorial. Looks like this. On bottom, 2 factorial is just 2 times 1. 2 factorial is just 2 times 1. So 2 times 2 is going to be 4. So that's really what I have. Now I can do this. So on top, all I really have to multiply is 6 times 5 times 3 times 2, which I could easily do. And that would give you the same answer that a calculator would give you if you put it in that format. All right, let's go down to this one. So counting permutations. So let me just lay out a couple things for you right here. So when you give you something in this format, 6P2, because there is a formula for this, but I'm going to show you maybe even an easier approach than using that formula. So 6P2, what does that look like in terms of a formula? Let me jump back to page 629. Here's what that formula looks like. So when they say 6P2, they're saying 6 factorial over 6 minus 2 factorial, or 4 factorial. Okay, and so we could certainly use the formula for that. It really wouldn't be that hard to do. However, it's just a little extra work. There are certain different approaches to this, and I'm going to show you what we could do. So first things first, 6P2. Guys, even though I can do this in a calculator, I still need you to know how the formula works because of cases like this where I can't put this into a calculator. They want me to just expand this using my formula. So let me lead into that. So follow along with the simple ones so I can lead you into what's going on in part C. So here's what 6P2 represents. If I just stuck with the formula, right? Based on the formula, I have n factorial over n minus r factorial, which if I clean that up is just 6 factorial over 4 factorial. Here's how they simplified this. This is what I need you to see. If I simplified 6 factorial over 4 factorial, what would that look like? So here is 6 factorial. Here is 4 factorial. What could I obviously cancel here? As I look at the top and the bottom, right, where I had the 4 factorial is going to cancel out with all of this. So if those guys cancel, we're left with just 6 times 5, which is 30. Right, and so that's what they did here to simplify that and get 30. Okay, so here's something else I want you to see on this. When I say 6P2, here's another way to do this, and it leads right into this setup. We are starting with a 6, and I am going to count down for a total of 2 places. I'm starting with 6, and I'm going to count down until I have a total of 2 values. That's it. So that's another way to also get that same setup. So let me show you it again with this one. Right? When I say 10P6, what does that mean in terms of this process? And guys, I want you to see this. Don't skip this because it's going to help you when you get to this problem. Okay, so when I say 10P6, what I'm really looking at is 10 factorial over 10 minus 6 factorial, which is 4 factorial. Well, guys, what did you notice as these guys simplified, right? As you count down from 10 to 1, and as you count down from 4 to 1, the remaining 4 values will cancel top and bottom, just like they did here, right? As I count this down, 4, 3, 2, 1 up here is going to cancel with 4, 3, 2, 1 down here. So this is going to start with a 10, and it's only going to go to 5 because the 4, 3, 2, 1 will cancel. So if I really simplify that, it's just going to be that layout, because the 4 factorial here would cancel out with the 4 factorial here, right? And so that's all I'm really left with. The other way to see that is I started with 10. I'm going to count down until I have a total of 6 items. Started with a 10. Count down until you have a total of 6 items. And that's this. Right? And so we could certainly skip to this idea pretty quickly if we recognize that process. Okay, so now let me use this to lead you into part C. Notice that this is my n. And again, I'm going to start with this, and I'm counting down until I fill this many spaces. Okay, so I started with n. This would represent n minus 1. This is 2 less than n. That's 3 less than n. That's 4 less than n. That's 5 less than n. Right? So if this is n, this is n minus 1, n minus 2, n minus 3, n minus 4, n minus 5. Okay, and so when they give me something like this, where I have to lay that out, because obviously n is n, I can't put this into a calculator. It's not going to expand it for me if I'm not putting in real numbers. So what they want us to show with this is, so how do you lay this out formula-wise? Right? And so that's what I have. I have n, and I'm going to count down until I have a total of 5 elements. So start with n, that's my first element. Then I have 1 less than n, then 2 less, 3 less, and 4 less. And if you look, I have a total, I stopped there because I have a total of 5 elements, right? That's 1, 2, 3, 4, 5. So that's the way we could lay it out in terms of a formula. And here I was just giving a real number example, but I already did that here, so I took care of that. So that's what they want us to be able to do in a case where I need to be able to just expand it out and not come up with a real number. So let me give you 2 quick ones for practice. 7p4. Again, so if I want to evaluate this without a calculator, you know what? Let me show you how I could do it with a calculator first. If I'm going to put in 7p4, if you have this calculator, I'm just going to select NPR, and then now I can type in the N and the R. There's my answer. Super simple. Some calculators that have the NPR button, you might have to type 7, then hit the NPR, then hit 4, and then hit enter. So some of them will go in that pattern, so you might want to look for that too. But anyway, super easy on the calculator. So if I wasn't using a calculator, how would I do this? Again, I would start with 7, and I would count down until I had 4 places filled. Done. So there's 1, 2, 3, 4, so I got to stop there. Now I could multiply those 4 numbers together. So 42 times 20 is going to give me 840. So let's take that same layout and use it for NP6. So again, I would start with N. I'm going to count down until I have a total of 6 elements. So that's my first element. And then, of course, N minus 1, N minus 2, oops. Right, on and on and on. I'm going to shortcut it until I get to N minus 5. That's always going to be 1 less than this guy, because if I have 6 places to fill, I already filled the first one with just N. So here's my second place, third place. That would be my sixth place. Would be the n minus 5. All right, let me move on. So here's the second idea, is combinations. What's the difference? A combination is one where order does not matter, right? Permutations, and this is the main thing you want to remember here, is in permutations, order matters. In combinations, order does not matter. It does go a little beyond order. Let me throw in a couple more keywords for a permutation. It's not only order, but it's also a difference in value, like a ranking. So like if you're talking about, and they like to throw out things like this next one, president, vice president, and secretary. Those are not equal in rank, right? So if you have a difference in value or a difference in ranking, that is also symbolizes a permutation, right? So those are all kind of keywords. So permutations would mean definitely a difference in value, a difference in order, difference in ranking. If you're talking about medals in the Olympics, gold, silver, bronze, those are different in value, different in rank, and so those would be a permutation. Combinations are just a random group. It's a group. That's probably the best word I would use to describe a combination. It's just a group of stuff, a group of numbers where order doesn't matter. There's no difference in value, no difference in ranking. It is just a group. It's kind of funny if you think about like your locker combination. Well, if you have, let's just say your locker, to be very simple, let's just say your locker combo was 1, 2, 3. Could I put those in my locker as 3, 2, 1 and it would still open? No, because the order matters, right? So when you think about it, a locker combo is not a combo. It's actually a permutation. So it should be called locker permutations because the order does matter. If your locker combo is 1, 2, 3, you can't put those in any order you want. There's an order to it. So that's what sort of separates out these two ideas. So yeah, so actually a locker permutation, not combination. Quick notation, and then we'll get into these guys. Just like the permutation, combinations look the same, but it's a C instead of a P, and still represents your total that you have to choose from, and R represents how many of those are you putting in the group. So if I had a group of 20 students, and I need to see how many combinations of 4 could I come up with, like I want to put you guys into small groups of 4, well, how many different combinations could there be, right? So how many different groups? Well, if I had 20 students and I'm putting them into groups of 4, so 20C4. There's another way to write that. It looks like this. So you will also run into this notation, means the exact same thing as this. Just FYI. So first let's figure out, how do I know if something's a permutation or a combination? So how many ways could you select a president, vice president, and secretary from a club with 50 members? So again, I have 50 members, and I'm looking for groups of 3. A president, a vice president, and a secretary. However, because there is an order to this, then it's no longer a combination. It's not just a random group of 3 people. I'm actually applying different levels of title to them. So now it's a permutation. So this would have to be a permutation. We would say I have 50 members, and I need to select 3 of them for those different positions. So I have 50 people to choose from for president. But then after my president is selected, now I have 49 people to choose from for vice president. So I got 50 people that could be president. After he's chosen, now the remaining 49 could be vice president. After he's chosen, the remaining 48 could be secretary. So that's our permutation setup. But you see why it counts down, because these are difference in value, right? The person I choose for president is president, right? Not secretary, not vice president. They can't play any role. They're given a specific job. So let's go on to the second one. So 30 people try out for choir, but only 10 are selected. How many different choirs are possible? So you notice the difference on this one is I am just selecting a group of 10 people, right? There's no order to it. There is no difference in rank or value. We're not talking about lead singer. I'm not talking about different groups like soprano, alto, tenor. I'm not talking about those things. It's just a group of 10. There's no difference to those 10 people. So I had 30, and I am choosing 10 of them in groups. Let's go on to part C here. There's a formula for this. I'll just throw it into your notes right here. Looks a lot like the permutation with one minor twist to it. It would be n factorial over n minus r factorial times r factorial. So one thing you'll notice is when it comes to combinations, you tend to get a much smaller answer than you would with a permutation. Because if you look at the formula has an extra piece on bottom, right? And as you guys know, when it comes to fractions, when the bottom number gets bigger, your overall value gets smaller, right? And so your combinations tend to be much smaller than permutations do. So here's one that people always want to know. Okay, so what's the probability of winning the lottery? So I just picked the Super Lotto Plus. You actually have a much better chance of winning this than like the Mega Millions if you really looked at the options, but let me just show you. So California Super Lotto Plus. So the way that lottery ticket works is you have to pick 5 numbers from 1 to 47, and then you pick another mega number from 1 to 27. So they made it even extra harder by throwing this mega number in, because instead of just saying 6 numbers, it makes it harder for you to win when the mega number has to be a certain number separate from the group. So how many tickets are possible? So let's look at this one. I have to select 5 numbers from 1 to 47. The order in which I do that doesn't matter, and there's no difference in value to it. I can pick 40, then I could pick 8, and then I could pick 7. So I'm just taking a group of 5 numbers from 1 to 47. So I'm going to have 47 numbers, and I'm going to choose a group of 5. All right, or you could write it this way. I showed this notation up above. All right, that means the same thing, by the way, so you could write it either way. So 47C5. And I'm multiplying here, multiplying my options together, just like the counting principle. So then I also have to pick a mega number from the numbers 1 through 27. So now I have 27 numbers to choose from, and I have to choose one of those, which, guys, anytime this is a 1, that's your answer. So 27C1 is the same thing as just saying 27. But anyway, if we multiply those together, and I'll let you do this in your calculator. I already did it. So you get 41,416,353. So 416,353. So that's how many combinations are possible for Super Lotto Plus tickets. So then what's the probability of winning? I don't like when they say odds. Odds is different than probability. I could explain that, but let me just give you the quick answer here. Probability, well, there's only one winning combination here, right? So I have to get all of my 6 values correct in order to win. So there's only one way to win this. If I actually wanted to turn this into a probability question, which this isn't a probability question, but if I wanted to say, so what's the probability of winning? Well, it's 1 in 41 million, right? So that's the probability of winning, if we wanted to make it a probability. So there you go. That's your probability of winning a Super Lotto Plus. Maybe it'll happen to you. All right, so I go through this last example with me. It's the last one we're going to talk about that we're going to do. There's a new formula in here that I want you to see. So look at the first part of the question. I threw 2 questions in here. The first one is pretty standard. I'm going to Baskin-Robbins, which has 31 flavors of ice cream. We all know peanut butter and chocolate is the best. But anyway, I want 2 scoops of ice cream, different flavors. So how many ways could I do that? So let's just answer the first part. I want exactly 2 scoops. Give me 2 scoops. How many ways could we do that? Well, like let's just say you just keep it simple. Let's just say you want a vanilla and chocolate. Nobody orders those two, but let's just say that's what you wanted. I want vanilla and chocolate. Would it matter if they put vanilla then chocolate or chocolate then vanilla? Would you have a different bowl of ice cream? You would not, right? So it is a group of two. The order doesn't matter. You would have the same bowl of ice cream no matter which of the two flavors they put in first. It's the same bowl of ice cream. So it's a group of two. So I got 31 flavors to choose from, and I'm going to choose 2 of them. So that's what it would look like if I want exactly 2 scoops. But if I really wanted to look at all the possible combinations, right, that I could create as I walk into Baskin-Robbins. So I got this one big giant bowl in front of me. How many possible combinations could I actually choose? There would be a lot, right? So I could choose none. I could have a bowl of nothing in it, right? So I could, for this next part, out of the 31 flavors, I could choose nothing. Or, of the 31 flavors, I could choose a bowl of only one flavor of ice cream. Right? Or, and this goes hand in hand with the first part that we just did, out of all those 31 flavors, I could choose a bowl of 2, and I could look at all the combinations and ways that I could do that. I could keep going on this all the way to saying, well, of those 31 flavors, I'm actually going to choose all 31. Right? Creates a whole lot of combinations. So the shortcut on this guy is simply, and I'll show you the formula, is 2 to the power of however many items you have. So in this case, our n value was 31. So it would be 2 to the 31st power. So the idea for that is basically you're going down the line saying yes or no to each flavor, right? So it's like there's 2 options for each one. You're either going to choose it or you're not going to choose it for all 31 flavors. And so this is obviously the much shorter way to doing something like this. So you can see that formula on bottom of page 631. There we go. So it's the one right down here in this box, so you can check that one out, but that'll do it for you.